Welcome. In this lecture, we're going to be taking our code here that has more of a top-down player movement and converting it into a platform character type of movement. It's not really going to introduce new features of the Godot engine. It's going to be more code review, just kind of reviewing some stuff that we've already learned and writing a little bit of code. And there's going to actually be more of that in the rest of this section because you've already got a lot of the basics down from the previous sections. And so sometimes we're just going to end up having a little bit of work that we put in without actually learning brand new features in order to get this project to be a Metroidvania because there's just work involved outside of the new features and the new things that you'll be learning. And so some of the lectures will be more like that. I'll try and keep them short and break up in between the learning as well to try to help with the flow of the course. We'll start by creating some new variables up here. The first one will be gravity because we're going to need a gravity amount. Next, we'll do a jump force. And these values that I'm putting in are just values that I found. I've made the character a little bit floatier because it seems to make sense with the type of game that I'm making. The feel is pretty nice, and so we've got a lower gravity amount. You can see it's lower than our acceleration. And then we need a max slope angle as well for moving on slopes. And we'll set this to 46. The default is 45 and we want to be able to move on slopes of 45. But for some reason it doesn't quite work properly with the value of 45. I had to set it to 46 in order to make slopes of a 45-degree work. I also want to clarify before because I mentioned to you guys that the max speed was lower than the acceleration and then didn't actually tell you why, but I told you that I would. So we'll be doing that in this lecture. Basically, the reason is because move and slide already takes into account delta time. And so the motion vector that you pass into move and slide doesn't need to have delta applied to it. And so that's why when we clamp our motion right here, we don't times this by delta. However, your acceleration is independent. Our acceleration and our gravity actually are changing values that are independent of the motion once it gets passed into move and slide. Basically, delta needs to be applied to any value that changes over time, right? So our motion represents our velocity and how it changes over time. We don't need to apply delta to that because move and slide automatically does that for us. However, our acceleration and our gravity represent the change. This gets into calculus just a little bit, but the easier parts of calculus, mind you, it represents the change of our velocity. So not our velocity is the change of our position over time, right? And the acceleration and gravity are the change of our velocity over time. So that change, we do need to apply delta to it because move and slide only applies it to the velocity, which is our change in position over time. Hopefully that wasn't too complicated. Delta can be a tricky subject. But the basics are we need to apply delta to our acceleration and gravity, but we don't have to apply it to our motion. So let's start by, we're going to actually clean up some of our code in our physics process a little bit. And we're going to do that by using a bunch of functions. And I highly recommend writing what people generally refer to as self-documenting code. And to me, that just means instead of having something like a comment right here that says get the input vector like this. Instead of doing this, and then right here we would say apply the acceleration, or the acceleration. I can't type it out right now. And then right here we would just say like move. Instead of having all these comments like this, I recommend just making functions, and then your code comments itself. So we'll create a new function and call this get input vector. And I'm actually going to add a bunch of returns down here just to make this easier for you guys to see. And then we'll copy this code right here and paste it down in here, although I'm not copying the up and down part. And then instead of having the comment there, we just do var input vector equals get input vector, like this. And then we'll have this function return the input vector, return input vector, after we've gotten it. And so we don't need the up and down because we're going to be, it's a platformer now. We only need to get our input for left and right, and then we'll have a separate input for checking jumps. But this right here is quite easy to understand, right? Get the input vector and we get an input vector. We don't have to put a comment here because the code itself is a comment. And that's the idea that we're going for. So we'll say function. Now for this right here, we're also going to change this because we no longer need to apply motion vertically. We're just going to apply the horizontal motion. So that's what we'll call this function, apply horizontal, you might call it force or motion, force. And inside of here, we'll say if, and we want to pass in, because we need access to delta right here, and we need access to the input vector too. So we'll pass in those, input vector and delta. We'll say if input vector dot x does not equal 0, motion dot x plus equals input vector dot x times acceleration times delta. And you can see this is really similar to what we had up here, only we're only doing the x instead of the x and y. And then we'll say motion dot x equals clamp, motion dot x negative max speed and max speed. Once again, it's very similar to this right here. We're clamping it. So we can get rid of this. We'll just get rid of this whole thing here. We still need to do our friction though, so we'll create a new function for that in a minute. And then we can just call apply horizontal force, input vector, and delta. And once again, this code right here is now pretty self-documenting. It's easy to understand what this is doing without having a comment there. Now we'll apply our friction, apply friction. This will need an input vector as well. However, since we're using linear interpolate to apply friction, we shouldn't need to use delta. At least that's my understanding. So we'll say, if it does, we can update this part later, but I'm pretty sure we don't need to. So we don't need to pass in delta. We can just say if input vector equals 0. So if they're not pressing any buttons, input vector dot x equals 0, motion.x equals lerp motion.x 0 friction. So once again, this is very similar to what we had before. If they're not pressing any buttons, then we will set our x value to approach 0 at a rate of 25%, which is our friction value, 25%, 0.25. And that's how lerp works. Now we'll update the snap vector. Whoops, I'm getting a little ahead of myself. So now let's have a jump check. Oh, we want to create a move function too. Move. And all we're going to do is call motion equals slide motion. Maybe don't need this function, but it reminds me of how I used to do it in GameMaker. So a little bit of nostalgia there. Let's do a jump check. Jump check. This will check if the player is pressing the jump button and then jump if they are. So if, and here's some crucial information that we'll want to discuss. This is a little bit of new learning here. If you come into the kinematic body, you can see we have these functions right here called is on ceiling, is on floor, is on wall. These functions they'll return either true or false based on whether you're on the ceiling, on the floor, or on the wall. Now, how can it know that? How can it know what's a ceiling and what's a floor and what's a wall? Well, you actually have to tell it, and we tell it, let's just put pass here. We tell it inside of our move and slide function. So remember when I was telling you about the other arguments that we could use? The very first argument is called the floor normal, and by default it's sent to 0, 0, which is just no direction at all, which is why our character, which is what you would want for a top-down perspective. However, for a platform game, we want a floor normal that tells us which direction is down. Ironically, to tell the game which direction is down, we actually tell it which direction the floor faces. So which direction does the floor face? Well, the floor faces up. So we'll do vector 2.up. And that'll tell the game which direction down is. Then when we're inside of our jump check, we can check to see if we're on the ground using the is on floor function. So if is on floor, if input dot is action just pressed UI up. So if we just press the up key, motion dot Y equals negative jump force. And we'll leave it at that for now. We'll need to put this function up here in order to jump check, in order to run this code, to actually run this code. So make sure if you run your game and you run into issues, you might have forgotten to actually call the functions up here in the physics process. So make sure you remember to do that. Now we want to create a function for applying gravity. For this one, we'll say if not is on floor. We only want to apply gravity when they're not on the floor. Motion.y plus equals gravity times delta. And we need to pass in delta to this one, because our gravity it's our change in vertical speed over time. So multiply that by delta. Motion.y equals min motion.y jump force. This right here prevents our vertical speed, basically how fast we can fall, so that we can never fall faster than our jump force. And so it kind of clamps our vertical speed in the same way that we clamp our horizontal speed. We can jump and that increases our speed a certain amount, and the gravity will then pull us down, but then the gravity can never increase our speed past the jump force amount. And that's it. We can save and run the game. And our character should be falling, but they're not. And I just did the thing that I literally told you guys to watch out for, which is I didn't call the function that I wrote. So we'll call apply gravity delta. Run the game again. There we go. Our character now has gravity. And you can see the friction. The friction isn't working properly. Oh, we never wrote our, did we ever apply our friction? We didn't apply our friction either. Goodness gracious. We also only want to apply friction. This is a little bit of a preference thing, but I only apply friction if we're on the floor as well. So and is on floor. And then make sure we call apply friction. And order up here, the order you call these functions in is important to some degree. So I'm going to apply the friction after we apply our horizontal jump force. Apply friction, input, vector. There we go. So we should get a decent amount of friction. Now you're going to see a problem here. And I knew this problem would happen, and that's okay. But our jumping doesn't always work. Sometimes you press jump and the character doesn't actually jump. And it seems like I'm getting it every time now. There we go. It didn't work that time. The reason is because is on floor sometimes doesn't know that you're on the floor if there's not a downward motion continually pushing you into the floor. So if you, for example, applied gravity constantly, so if we removed this line right here, I'm just going to comment that out, and we constantly applied gravity to the character, then our is on floor would always be properly detected. And so I guess for now, we might just leave it at that. But we'll probably end up changing that later back to what it was at before. Let's, for a final thing, what we'll do, because we have a different fix that will fix that as well. For the final thing that we'll do in this video lecture, we're going to allow the player to control their jump height. So here we'll say else. So we first checked, are we on the floor? If we are, then allow the player to jump. Else, we can allow the player to cancel the jump mid-jump for a certain amount. And that will allow them to control the jump height. So we can say if input.isAction just release. So they just release the up button, UI up. We need to add some more information here, and motion.y is less than negative jump force divided by 2. So what is this line? Well, this line just makes sure that we're still actually going upward when we release the key and that we haven't slowed down. You know what? Let's remove this line and I'll just show you what it does. Motion.y equals negative jump force divided by 2. So this says if we let off the jump key mid-jump, then it will instead of setting our jump force to negative jump force, it'll be negative jump force divided by 2. So the player can cut their jump height in half if they release early, right? So you can see if I tap the key, we barely jump, and if I hold the key, we jump really high. However, the problem is if you release at the very top of the jump, you can get a little extra jump height. And if you release while you're falling, you can also jump just a little bit more before you land on the ground. However, with our magic check right here that I had, and motion.y is less than negative jump force divided by 2, this makes sure that the character is still going upwards and that their jump force hasn't exceeded or hasn't been reduced past this amount. So when we apply that, it allows us to cancel our jump, but to never actually release it when we're falling down. If we're falling down, then our motion.y is going to be greater than this value. And so, because downwards is actually positive and upwards is actually negative. So as we're falling down, this value is going to be positive. And that prevents us from doing the little tap release that we saw earlier. So that's going to be it for this lecture. We've got a nice little basic character moving. And I think it looks pretty good. Little platform character already with, I would say, very few lines of code. We've got, 48 lines of code here. Pretty clean code. Hope you guys enjoyed this lecture, and I will see you all in the next one.